Ah, this is black hole mathematics. I will prove what I have told. First, main result. Dimension of a sphere with volume divergence. Notification. S3D is a sphere with volume divergence, and ds3D is the boundary of a sphere with volume divergence. And SV1 is a sphere with volume 1, and dsv1 is the boundary of a sphere with volume 1. This is the first theorem. If dsv3D exists, dsv3D is homeomorphic with four-dimensional Euclidean space. If dsv3D exists, dsv3D is homeomorphic with four-dimensional Euclidean space. 4D Euclidean space is a metric space with four independent variables, and this is a usual four-dimensional space we usually say. So we can say dsv3D is four-dimensional. Let's prove it. To show they are homeomorphic, we must show first that there is a function from ds3D to four-dimensional Euclidean space, and the function should be one-to-one correspondence, and both the function and its inverse function should be continuous. To do that, we define the spherical coordinates inside the S3D. Assume three independent vectors which originate in the center of S3D, and in orthography and normalization, these vectors can make a rectangular coordinate system. And this three-dimensional rectangular coordinate system can be translated into three-dimensional spherical coordinates. Now, in this spherical coordinate, we can define an angle theta phi. And within this angle, we can project a point from the center of S3D to ds3D. Then, I can call the projected point as theta phi, and we will call this point as A. First, we will show that ds3D has four independent variables. And I will call a point near A, which is on the ds3D, as B. Then B is on the surface. So, to express B, I can use polar coordinate, which originates at A. So B is expressed as omega L, where L is a finite length from A, and omega is an angle which specifies the specific point within a distance L from A. And to express B, we first define A, so B is expressed as theta phi omega length, which is a sum of coordinates of theta phi and omega L. Now, we will show the four coordinates are independent. So, we should show that theta phi independent with omega L. First, see length, the finite length between A and B. We will show that if length can be expressed with theta phi, then there exists a contradiction. Assume L was expressed with theta phi, and the equation expressing the area of ds3D is 4 pi r squared, where r is the radius of a sphere, and r is infinite. So the area of ds3D should be infinite. And if you express an area of a circle inside, it is 4 pi r squared. This is arrived at by multiplying the radian to the area of ds3D, but multiplying number to infinite value produces infinite values. but the area of circle within the radius R is finite, so there exists a contradiction when we assume R is expressed with theta phi, so R and theta phi are independent. Now we will show that omega and theta phi are independent. First, assume omega can be expressed as theta phi and assume a function like this. And R is the length value in spherical coordinates of SVD, and I is the length value in spherical coordinates of SV1, and theta phi is the angle value in spherical coordinate of both systems, and R is between 0 and infinity, and I's value between 0 and 1. And R is the length from origin in the SV system, and I is the length from origin in the SV1. And F is a function which goes from sphere to sphere, so the angle value set phi on the boundary of a sphere is conserved within F. And within F, the length value is conserved within regard to the small and large relation. And with F, the finite circle in the DS3D goes to a point in the DS3-1. Now, we will prove this. The value of delta theta, delta phi is conserved in the F because F conserves the value of theta phi. And the finite circle on the DS3D is always smaller than 4 pi r squared delta theta, delta phi, which is infinite. And because theta phi is conserved if F, so the value of 4 pi r squared delta theta delta phi in this 3D becomes 4 pi delta theta delta phi within F. So F value of the finite circle on the DS3D should always be smaller than 4 pi delta theta delta phi, and the circle which is smaller than every other circle is a circle with zero side. So the circle which has finite F value on the DS3D goes to a point on the DS3-1. And here, omega is an angle value which pertains a point on the boundary of the circle. And we assume omega can be expressed with theta phi, and F conserves theta phi. Then, when a finite circle on the DS3D goes to a point on the DS3-1 within F, the omega value which is expressed as theta phi conserves. Then the point on the DS3-1 should have omega value which is expressed as theta phi. This means the point has a two-dimensional value. And in this contradiction, so omega and theta phi are independent, so theta phi omega lengths expressed on DS3D are four independent variables. And consider the next function, f and its inverse function is like this. Then f is a function from DS3D to four-dimensional Euclidean space, and it has one-to-one correspondence and is continuous. And the inverse function is a function from four-dimensional Euclidean space to DS3D, and it has one-to-one correspondence and is continuous. So DS3D is four-dimensional manifold. And also, if I put another angle on DS3D, the angle should be independent from other coordinates. So we have four independent coordinates on the surface. Bulk of S3D is four-dimensional. Now, I will explain theorem 2.1.2. We will use Poincare definition. Let's see the definition about dimension by Henri Poincare. One dimension is a zero-dimensional X section. 2-dimension is a 1-dimensional section, and 3-dimension is a 2-dimensional section, and 4-dimension can be defined as a body whose section is 3-dimension. And by mathematical induction, 4-dimension can be defined as a body whose section is 4-dimensional. Now let's put this definition to theorem 2.1.1. dsVD is a section of SVD, and dsVD is 4D manifold, so the bulk of SVD is 5-dimensional. Next, I will see theorem 2.1.3. A circle with finite area on dsVD is a plane. dsVD has a curvature as 1 per r, and r has an infinite value, so the curvature of dsVD is 0, so the finite circle of the dsVD is on the plane. So, we proved the sphere with volume divergence is 4-dimensional and the surface is 4D plane. Next time, I will prove black hole is a sphere with infinite curvature. So, black hole has 4D plane surface and 5D bulk. And this way, I will prove AJ-CFT correspondence theory in a mechanical energy. Bye. Thank you, my friend.